Hey, I just want to welcome everybody to our first enviroCHAT for 2021. We'd love to do these in person as soon as we can safely do that. We're going to start as soon as possible on those too. I just want to do a couple of quick updates for the EMA. We do have science fair judging the first week or so. There's a kind of virtual science fair judging. We're still looking for judges as well. Please let us know if you're interested, especially for those who've done it before. Interested to let you know I did sign back up again today myself. So, and I know a guy from our office is also involved too. The next item I have is keep the date open for our golf outing. It is on July 12th that we're going back to Dearborn Country Club again. And then look forward to like ongoing emails for like future events that we're going to be involved with this year. And as soon as like things start opening back up again, we're going to really try to be as active as possible because really people miss the interaction of in person. And I know I really do. With that, I'd like to introduce Johnny Neal. I first met Mr. Neal, I'm trying to think of how long ago, in the early 2010s at Wayne Assembly. And then since that point, he moved on to greener pastures at Ford Rouge, and we kind of assisted Dearborn Truck and Johnny in regard to his zero waste initiative at that plant. And then I always respected Johnny, but now even more so looking at his bio, like he's an Eastern grad. And I always have a place in my heart for anybody who went to Eastern. And I always think that when you're looking at different folks and what their abilities are, strengths, but if you're an Eastern grad to generalize, you always get things to the finish line. And Johnny was one of those guys who did that as well. So with that, Mr. Neal, the floor is yours.
Thanks, Mike. That means a lot coming from you. I think I actually might have run into you a little bit before Wayne Assembly. Even I'm not sure. Did a little work out in Saline and whatnot too. So it's been a while though. It's been a while. So I want to say thank you, and it's my first time presenting here for the EMA. And as Mike's mentioned, my different workings at different facilities have kind of gotten to me where I'm at now. And currently, I'm working with a team at DTE on the company's biogas to renewable energy assets, and we're doing a lot of cool things within the renewable energy space right now. And Mike thought it might be interesting if I share with you guys some of our recent activities, kind of especially in the area of converting dairy cow manure into green renewable energy. So you go ahead and next slide. So DTE Biomass Energy has been around for about 30 years now, creating renewable energy from waste gas and primarily landfill gas. So we're headquartered in Ann Arbor, Michigan, and we currently operate 30 different biogas to energy projects across the United States. We currently have about 80 employees working in this division. So these projects either use biogas as fuel, where we make electrical power, or we clean up the biogas and convert it into a product that looks just like natural gas, which moves through our nation's pipeline and transmission system. You can go to our next slide. So we have a fairly meaningful footprint in North Carolina here, and I know Mike kind of wanted me to touch base on this a little bit because where most of our we have a large group of sites in one area here, and we operate 6 different projects across the state, with one of our oldest projects, which is Salem Energy, dating back to the 1990s. So all our projects here in the state, they take biogas, which is generated at landfills, and use as a fuel to drive our engines or turbine-driven generators to produce renewable electricity. You can go to the next slide. So I thought I'd set some high-level context relative to the external environment. So I'm sure everyone's familiar with the discussion around global warming, reducing greenhouse gases, and generally decarbonizing not only the US, but the planet. And really what this means is that we're reducing the byproducts that result from the combustion of fossil fuels, for example, to make electricity, to power our vehicles, and natural occurring compounds such as methane. And all these compounds contain carbon, thus leading to the term decarbonization. So this slide is simply just meant to show the significant tons of carbon dioxide equivalents, which must be reduced over the next 20 years in order to stop the rise in global temperatures by, say, about 2 degrees. So what's challenging here is that this reduction translates to about a 4.5% reduction in emissions each year. And an interesting fact is that's really only been achieved once since 1990. So we've got a long road ahead of us. Moving on, next slide. So achieving carbon emissions reductions of this scale is going to require some significant changes to all sectors of the economy, not just the power sector. So we need to start developing new cleaner transportation fuels, electric vehicles. We need to have energy efficiency improvements, which would be the third one down here. And changing our industrial processes. So including, for example, capturing the carbon dioxide that's emitted into the atmosphere and storing it underground, which is an active thing that is currently being done as well. Go to the next slide. So what we do has a pretty meaningful impact on the reduction of greenhouse gases as we work to capture the methane generated at landfills and as part of our manure management at dairy, swine, and chicken farming operations. So methane, which is 23 times more potent than carbon dioxide as a greenhouse gas. So anything that we can do as part of our business is even more impactful than reducing the carbon dioxide. So the two pieces on the left-hand side of the pie here are mainly what we work on, which is the landfills and the manure management, equaling 26%. But also an interesting note on the slide is that the enteric formation, or the bottom pie piece of the pie there, which is methane that's produced from animal flatulence and thus it can't be recovered, makes up nearly the same amount of methane as what we're trying to focus on here as well. You can go to the next slide, please. So when organic waste streams like animal manure, landfills, agricultural waste, and food processing waste decompose, biogas, which is principally methane, can be converted to a beneficial use. So as landfill-based projects have been our bread and butter for the past 30 years at DTE, and everyone always asks, how do you create the biogas? I thought I would give a quick biogas explanation. So biogas is roughly 50% methane and roughly 50% carbon dioxide as the two major constituents. And if controlled, landfill gas contributes to smog and global warming and may cause health and safety concerns. So that's landfill gas, right? But what is technically a current landfill? So 30 years ago, regulations mandated and defined what we now consider them as a sanitary landfill, something with some major components to it. The old time before the modern sanitary landfill, they were technically called dumps, and we really try to stay away from that term now. I don't know, Mike, if you still consider them that or not, but
I would definitely consider it just a dump. It's exactly that. Everything just got dumped in, no liners, no collection methods, just what you used to see like kind of in the movies. That's what it's like. Nothing like that now.
Yeah, back it up to a hole and dump it in, right?
Yeah.
So incineration and dumps are undesirable pretty much from a sanitary standpoint, odor, smoke, and an air quality perspective. So there's these main components that I was talking about to create a sanitary landfill. One of them would be the liner, right? So we have a clay and synthetic structure at the bottom of the landfill, which prevents the water that drains through the trash from polluting the groundwater. And on this figure here, it's shown in a red line on the bottom. Then we have the leachate removal system. So leachate, which is the water that's leached through the trash and through the hill, must be removed as the liner prevents draining, and it must not threaten the stability of the landfill, right? You have to control how much leachate you have in the bottom collection area. So this is shown as the gray lines that are running along the top part of the liner lines. And third, we have the gas collection wells. And this is a slotted well pipe that's inserted in the trash mass, and then there's a vacuum applied to that well, and it pulls it to a central point. These wells are drilled into the landfill at sometimes, and I've seen them at about a 3-foot diameter. They get drilled down into the center of the landfill, 40, 50, 60, up to 80 feet. There's some rock packed into the granular space, and it pulls the landfill gas, biogas. Next slide, please. So we take that biogas that we collect from our landfills, and we generally use it as fuel. So that fuel is used to power either a large internal combustion engine or a gas turbine engine, which is connected to an electrical generator, where we then in turn produce electricity and we put it back into the grid. So pictured here on the right is our plant in North Carolina's URE National Forest. This is actually one of my personal sites that I manage. There's enough biogas here coming from the landfill to run 6 12-cylinder engines all at once. And it's quite a facility. The photo on the left is a large gas turbine plant that we operate similarly outside of Los Angeles. So we are technically coast to coast. Next slide, please. So we obviously integrate a bit differently at a dairy farm. This is where we're going to start to transition a little bit into the different type of work we are starting to get into here. So there's similarities between the dairy farms and landfills, meaning the biogas, which is still roughly about 50% methane, 50% CO2. It's also anaerobic like landfills. We have a lack of oxygen, but we do have a little bit of sulfur that also comes from the manure. So currently we have contracts with large dairy farms, and by large, I'm meaning 5,000 to 9,000 head of cattle. These farms are very well run, and the farmers work very hard to maximize the value from everything they're doing. So the dairy cows that are at these farms, along with producing up to 6 to 7 gallons of milk per day per cow, produce between 40 to 150 pounds of manure per cow a day as well. So without a digester, a farm would usually collect manure in a lagoon and then can land apply it for use as a fertilizer, as in a liquid spray, or use it as direct implementation. And that's good, but part of that process is a lot of methane is emitted into the atmosphere when we have these open lagoons. With a digester, which is on the right-hand side of this figure here, the manure can first be directed through the digester, where the biogas is created as the manure decomposes anaerobically, just like the waste does in a landfill. And this is what we want, right? Like landfill gas, biogas is primarily methane, it's CO2, and a little bit of H2S, like I mentioned before. So for the farm owner, manure through a digester provides a few benefits. One, the manure coming out of the digester, which is referred to as digestate, it doesn't smell as bad as the volatile pathogens, have been destroyed out of the manure. So this is kind of good for community relations, right? The smell isn't as bad. I know, Dan, I know you deal with some farm fields out by you in Fowlerville area, so I'm sure you're used to that. And the second is it reduces the material to the lagoons as biogas is produced. So the less land that's needed for a lagoon, the land holdings can drive the herd count. So less space needed for lagoons creates more space for more cows. And also some farms use the remaining solids as a bedding material for the cows. And I'll have a picture later on here that kind of shows that we're trying to use every single aspect of the process. And of course, DTE also has a royalty or a fee paid to the farmer for the manure rights. So it economically benefits the farmer as well. Next slide, please. So I've showed you how the biogas is created, but gas is captured and processed into the pipeline quality standards using well-proven technologies. And the RNG, which is renewable natural gas, can then be transported into the nation's existing pipeline infrastructure and be delivered to fueling stations that are designed to pump the liquefied or compressed natural gas into vehicles. So we're going from farms to vehicles. Next slide. So let's talk a little bit about the equipment we use to produce this dairy biogas. So the manure or liquefied mixture, which is generated continuously at the farm, is directed to large tanks, which we call digesters. And these structures can vary in size and design. So the cartoon here that I show is an above ground structure, and it's fabricated from steel or concrete. The digester can also be below ground, with manure stirred and transported in a less continuous fashion. It's more of a snake back and forth type design when it's buried underground. So we have large mixers that are shown on the right side here that keep the contents continuously stirred. We also have heat from some source that must be added to the digester so as to maintain the 95 to 105 degree temperature range that keeps the bacteria happy and growing and helping produce that biogas. So this is typically done via heating fluid, which encircles the tank. And on this picture here, it's the orange coils going around the tank as well. Next slide, please. So manure on average resides in the digester for about 20 days. And that's really how we design these tanks, is to hold the maximum amount they can for the 20-day period. So the tanks pictured here in this photo are 800,000 gallon tanks. And we have some of our newer ones that are around 1 million tanks. And I've even seen some design specs for ones that go all the way up to 2 million gallons. The digesters here in this picture are about 30 feet high and 60 feet in diameter. What you see pictured in the center here and to the right are the digesters, and they're kind of dome fashioned, with the roofs are expanding roofs, which are kept up by the pressure of the biogas. On the bottom left-hand corner are the pathogen-free, fully digested solids that remain that can either be used for fertilizer or for animal bedding. Once again, they don't emit the odor that they have before because all the pathogens have been removed. So finally not pictured is the remaining digestate, which then gets returned to the farm, ultimately for reuse as a spray fertilizer application. Once again, trying to use all the products we can. Next slide. So now that we've generated the biogas, we need to clean it. We need to polish it. We need to convert it to pipeline quality renewable natural gas, which can then be injected into the pipeline for transportation to market. So there's several technologies here to accomplish this, but at DTE, we use a membrane system that separates the desirable constituent, namely the methane from the biogas stream from the digester. So the slide here shows both a cartoon and an actual cutaway image of a membrane bundle. The membrane can be described as a bundle of 1,000 microscopic porous straws. And that's a cutaway on the right showing the fiber bundles. So in a single commercial scale cartridge, the fiber length can be as long as 1,000 miles. The individual components of the gas have different diffusion rates through the walls of the membrane. So this allows for a controlled separation of the gas. So the methane moves through the straws lengthwise to the other end, while the less desirable contaminants, CO2, H2S, permeate through the walls of the straw, where they're then directed to a flare for destruction. Next slide. So this is an image of a membrane skid that we have at one of our facilities in Wisconsin. On the lower left-hand side of the skid are those long cylindrical tubes that you see, and those are each a single membrane. The other equipment you see in the picture, the steel tubing, is tubing that we use to bring the renewable natural gas back up to pipeline quality pressure. Next slide. So we've created the biogas, and now we've cleaned it and polished it, and we've turned it into a pipeline quality product. We now need to get it to the market. So very often these dairy farms we're working on are in very rural areas, and they're not near a point where we can conveniently and economically inject it into the gas pipeline. So what we've done at numerous sites is we've employed a virtual pipeline where we truck the RNG to one centralized injection facility located atop the pipeline. So the RNG can be created at the farms, compressed, and loaded into these tube trailers. Each one of these trailers has 4 long cylindrical tubes in it. And these trailers are specifically designed for such operations and are pretty costly. Each one of these trailers is roughly $500,000. And they're standard 53-foot trailers, but they operate at a 300 or 3,600 PSI pressure. So our system will fill one trailer, and once that trailer is full, we'll automatically switch over to the second trailer. And at that point, we contact a driver to come pick up that first trailer and truck it to our station that applies it atop the pipeline. And mainly because dairy farms are a 24-hour operation, we always have someone on call for this. Next slide. So now that I've given you the details on our assets, I'd like to leave you with one of our most recent projects. This is our recently constructed New Chester facility in Wisconsin. And to kind of give you a sense of scale, the silver roof, the one in the back behind the domes, it kind of looks like a lake in this picture, is one of the barns used for housing the cows. The white buildings are the gas process buildings, as well as the flares that are out front of the digesters. So this site is now fully operational. And I believe these are 1 million gallon digesters each. So I want to thank everyone for their time and interest today listening in. If you guys have any questions, I'll do my best to answer them here.
Yeah, I'll start off like with the recent, like Texas, my daughter lives in Dallas. So like she lost power for a few days. What's the consistency of like the gas out of these compared to like what they're dealing with, like wind and solar down there?
So from what, I mean, these are proven to be very consistent. We're operating these in cold states, right? Wisconsin, where a lot of these dairy farms are at. They're kept at a pretty consistent heating level. So we're not worried about anything really freezing up on us, right? As for solar, I mean, even solar in wind, wind power in Michigan is even, it's not continuous. It's generally 20–30% of the time it's generating electricity. So this is something that is continually ongoing, Mike. It's got a pretty good success rate.
Terrific. And then like, I'll just chime in one more question, then I'll be done talking for the day. I know I've like been involved with other digesters. We have one dairy farm we're working with right now, but other ones that take food waste in. You have very consistent volume. Obviously it's all the same. But these food guys are very particular on what they take in. What's the difference in the process of that type of biodigester compared to yours?
I think with the food, and this is just what I thought of kind of the top of my head here is a lot of the food digesters, they're probably seeing different contaminants, Mike, that are coming into where we can control and we know exactly what's coming in, right?
Mm-hmm.
So in our membrane system, we know exactly what we're trying to pull out. So I think that's where they might get particular is the way that they clean and polish their renewable natural gas is a little bit of a different process.
Got it. Okay. Anybody else?
Hey, Johnny, are you guys doing these at all? You're doing it with dairy farms, but what about human wastewater plants? Any reason that couldn't be applied there?
That's a good question, Dan. I know we aren't really doing anything, I think, with like wastewater facilities or anything like that yet. I think that's probably coming along the way as we need to do some carbon sequestration and different projects. A lot of it I know right now has to do with what's the cost, right? So is it worthwhile to put one of these in? And funding for that type of thing too. So where we know like one of these facilities is roughly, $2 million to put in just for a smaller one, knowing we're going to get a return on that. So if we work with a local utility, I'm not sure exactly how that worked, but that's a good question, Dan. I'm unsure.
Well, and that's obviously coming. There's the one up at Flint where they're attached to the septic system up there, but then they're also taking food waste, and they've got a little more flexibility on what they can receive. And I could see that being certainly an opportunity in the bigger cities to help with this whole, organics stream that folks are trying to get moved forward.
Yeah, absolutely. I mean, right now I know we're working, we do some work at some chicken farms and some swine farms as well. But like I said, we know that it's a consistent waste stream and what exactly is coming in. So I'm sure we'll get there. I'm sure we'll probably work with someone and kind of start venturing towards that direction. Good question.
Hey, Johnny, is this strictly batch processing? Those digesters seem to be, for the most part, pretty good size volume wise, or can you add material throughout that 20-day cycle or no?
Yeah, so you can add material through that 20-day cycle, Kurt.
Okay.
Yeah, so it's continuous, and once we do fill up a digester, we rotate to that next digester after that. So
Okay.
It's not exactly a 20-day, we open it and then we close it after 20 days.
Right.
You add to it to help. Yeah, we add to it to help the pathogens kind of keep going and keep that batch working, right? It's just a larger batch, I'd say.
Okay, that makes sense.
Mm-hmm.
Is this something that you guys, is it a joint venture like with the dairy farmers, or is it something that like DTE is completely financing their way, or the local utility?
So it's mainly just DTE. We do get a little bit of tax credit because we are pretty much a negative emissions facility then. So we do get a tax credit for putting these in.
And how long does it take to get one of these from like start to finish once you ink that deal? I mean, those things are huge.
Yeah, they're pretty big. So depending on the size, right? Depending on the size of the farm. If we have one that is simply the one I showed earlier, they had the 2 concrete digesters. Yeah, that one may have taken about 12 to 16 months from inception to completion. Yeah, some of the larger ones can take up to 2 years.
Anybody else? All right. Hey, Jenny, really thank you a lot for doing this today. I really do appreciate it. We'll invite everybody out to the next enviroCHAT that we have. And I'd love to see everybody in person when we do it. And then I'm hopeful that maybe in the next couple of months, but after that, like maybe we like during the summer, and then for sure, like in July for the golf outing at minimum. So thanks everybody and have a great day. Okay.
Good to see everybody.
Okay, everybody, appreciate it.
Thank you.
Yeah, very nice job too, Johnny.
You guys learned something today.
Always.
Great.
Thanks, Johnny.
Thank you.
Go Hurons.
Go Eagles.